In this lecture, we are going to learn about neural networks. So we will start with an introduction to neural networks. What are different types of activation functions and types of neural networks? We will then discuss perceptrons and how to build a classifier based on them. After that, we'll go deeper and learn about single layer neural networks and multi-layer neural networks. One of the fundamental premises of AI is to build systems that can perform tasks that would normally require human intelligence. The human brain is an amazing model at learning new concepts. So why not use the model of the human brain to build a system? An artificial neural network is a model designed to loosely simulate the learning process of the human brain. Neural networks are designed such that they can identify the underlying patterns in data and learn from them. They can be used for various tasks such as classification, regression, and segmentation. But one major drawback of neural networks is that we need to convert any given data into a numerical format before feeding it into the neural network. For example, we deal with many different types of data, including visual, textual, and time series. So we need to figure out how to represent problems in a way that can be understood by neural networks. To understand this process, let's first consider how to build a neural network. But before jumping into that, let's go through some use cases, different activation functions, and types of neural networks. So coming to the examples, first is chatbots. The chatbots that we use in our day-to-day life have an underlying neural network model that's working. Then comes natural language processing, translation, and language generation. These also involve a lot of neural network processing and modeling. The third is image detection, and fourth is facial recognition, and so on. Now, coming to the activation functions, an activation function decides whether a neuron should be activated or not. So it is just a function that you use to get output of a neuron. It is also known as a transfer function. It is used to determine the output of neural network, like yes or no. It maps the resulting values in between 0 to 1 or -1 to 1, depending upon the function. The, the activation functions can be basically divided into two types. The first is linear activation function, and second is non-linear activation function. So linear activation function, this function is just a line and it is linear. Therefore, the output of the functions will not be confined between any particular range. So for example, the equation for it is f of x equal to x, and its range is from -infinity to infinity. Now coming to the non-linear activation functions. So on the other hand, non-linear activation functions are the most used activation functions. They make it easy for the model to generalize or adapt with variety of data and to differentiate between the output. The nonlinear activation functions are mainly divided on the basis of the range or curves. So for example, we have sigmoid or logistic activation functions. We have tanh or hyperbolic tangent activation functions. Then we also have rectified linear unit, which is the ReLU activation function. And fourth is leaky ReLU. Now coming to the types of neural networks. First one is deep neural network, or more commonly known as neural network. It is basically a neural network with more than one hidden layer. Next is convolutional neural network. So convolutional neural network, each neuron in the next convolutional layer is connected only to the neurons located within a small rectangle in the previous layer. Then comes recurrent neural networks. So recurrent neural networks form the basis of forecast models and language models as it handles the sequences of data. The most common is the LSTM, which is long short term memory, and GRU, gated recurrent units. Now coming to GANs, which are generative adversarial networks. These are designed to create new data instances that resemble the training data. GAN has two components, a generator, which learns to generate a fake data, and a discriminator, which learns from that false information. Now, building a neural network. Some components of human learning process are hierarchical. We have various parts in our brain's neural network, and each stage corresponds to a different granularity. Some parts learn simple things, and some parts learn more complex things. Let's consider the example of visually recognizing an object. When we look at a box, the first part in our brain might identify simple things like corners and edges. The next part identifies the generic shape, and the part after that identifies what kind of object it is. This process might differ for different brain functions, but you get the idea. Using this hierarchy, the human brain separates the task and identifies the given object. Now, to simulate the learning process of the human brain, the neural network is built using layers of neurons. These neurons are inspired by the biological neurons, which we previously discussed. Each layer in a neural network is a set of independent neurons, and each neuron in a layer is connected to neurons in the adjacent layer. The first layer is the input layer, the last is the output, and the middle layers are known as hidden layers. Now let's go and look at perceptron-based classifier. So a perceptron is a fundamental building block in many neural networks. It takes inputs, performs computation on them, and then produces an output. It uses a simple linear function to make the decision. Let's say we are dealing with an n dimension input data point. A perceptron computes the weighted summation of those n numbers, and it then adds a constant to produce the output. The constant is called the bias of the neuron. It is worth noting that these simple perceptrons can be used to design complex deep neural networks. Now, let's jump into the notebook for the demo. So for the perceptron classifier, we have created this IPYNB file. First, we load the input data from the text file, which is data perceptron.txt. Each line contains space separated numbers where the first two numbers are the features and the last number is the label. Now, you first import the required libraries, which is NumPy, Matplotlib, and NeuroLab. After that, we separate the text into data points and labels. Then we plot these data points, and then we define the maximum and minimum values at that each dimension can take. Now, since the data is separated into two classes, we just need one bit to represent the output. So the output layer will contain a single neuron. We have a data set where the data points are two-dimensional. Let's define a perceptron with two input neurons where we assign one neuron for each dimension. Then we train the perceptron with the training data. And finally, we plot the training progress using the error metric. And this is the output. Now, having a model that has a few perceptrons is a good start, and it allowed us to get a fundamental understanding of this exciting concept. But to really solve problems, such a simple model will not be sufficient. The human brain has approximately 85 billion neurons. Obviously, we won't be building a neural network that has that many nodes, but this number gives you an idea of what it takes to solve complicated problems. Before we build a model with billions of nodes, let's take the next step to building a new network with a single layer. This single layer neural network consists of independent neurons acting on input data to produce an output. So let's get to it. So we first created this IP1B file and imported these following packages. We are using this NeuroLab package. We'll use the input data from the file data sample. We'll use the input data from the file data underscore simple underscore nn.txt. Each line in this file contains four numbers. The first two numbers form the data point, and the last two numbers are the labels. Now, why do we need to assign two numbers for labels? Because we have four distinct classes in our data set. So we need two bits to represent them. So let's go ahead and load the data. So after we load it into the text, we separate the data into data points and labels. Then we plot the data, and then we extract the minimum and maximum values for each dimension. Now we define the number of neurons in the output layer. Now we define a single layer neural network using the above parameters. Then we train the neural network using the training data, and then we plot the training progress. Now we define some sample test data points and run the network on those points. Now, as we can see, the error quickly starts decreasing, signifying that our training is efficiently creating better and better predictions. In this case, the error did not go down to zero, but if we let the model run for a few more epochs, we expect that the error will continue to decrease. So we enhanced our model from a few nodes to a single layer, but we are still far away from 85 billion nodes. Obviously, we won't get to that in this section, but let's take another step in the right direction. The human brain does not use a single layer model. The output from some neurons becomes the input for other neurons, and so on. A model that has this characteristic is known as a multi-layer neural network. The type of architecture yields higher accuracy, and it enables us to solve more complex and more varied problems. So let's get into a notebook. Here again, like the previous sections, we are using the same neural lab module along with NumPy and Matplotlib. Then, unlike the previous sections, we are now generating some training data over here. Now we reshape the preceding variables to create a training data set. We then plot the input data and then define a multi-layer neural network with two hidden layers. Then we train the neural network using the training data that was generated, run the neural network on the training data points, and then plot the training progress. Now, the then we plot the predicted output. As we can see over here, this output is basically your input data. Here we are basically showing the training progress. And this third output is basically the predicted output overlaid on top of the input data. Now, the predicted output seems to follow somewhat closely the actual input. If you continue to train the network and reduce the error, you will see that the predicted output will match the input curve even more accurately. So that's it for this lecture. Thank you.